Check this out. We've got something really fun today. This is so amazing. Oh man, again? 8.2 transformations of logarithmic functions. Just like our other functions, our vertical stretch and reflection will be outside, and our vertical translation will be outside, and our horizontal stuff will be inside. The base of the log is not eligible for transformation. If you change that, you're just creating an entirely new function. We want to transform y equals log base 2 of x into y equals a times log base 2 b times x minus h plus k. We're not given the exact values of a, b, h, and k, but we are given that a and k are greater than 0 and b and h are less than 0. So let's draw this, or at least figure out what it would somewhat look like. If a is greater than 0, that means that this could be stretched taller, or it could be stretched smaller, or it might not be stretched at all if a was 1. So I'm not going to do anything with that part of this graph. The next one is b is less than 0, and that means that, again, it could be stretched horizontally, but it might not be. We do know that there'll be a reflection. So I'm going to try to flip this over. There we go. And it's flipped over the y-axis. So it will look something like that. Now h is less than 0. That means that we have a horizontal shift left by h units. And I don't know what h is. -1, -2, -3. I don't know. So I'll just put it here. Next we've got k is greater than 0. That means we've got a vertical shift up of k units. And again, I don't know what k is, so I'll just slide it up here. And that looks good enough. So my new graph looks something like this. And I'm just going to scratch out the numbers here. This isn't going to be -3, -2, -1. This will be, just so I can remember, this is h units left. So this would be h, whatever h was here. So hopefully that gives us an idea of what this transformed graph looks like. Now let's try to answer the questions. What is the equation of the asymptote? So it's still a vertical asymptote because logarithmic functions have vertical asymptotes. And it's not at -3, remember I crossed that out. So the vertical asymptote is at x equals h. Now it's not -h. I see a lot of students doing -h. Look, h is negative in and of itself. So if you put -h, that would actually make it positive. So that's not what we want. What is the domain and range? So let's do the domain first, and we'll do it in interval notation. So it looks like it goes all the way from -infinity to h, not including h either. And the range looks like it goes from -infinity to +infinity, so all real numbers. Now what is the x-intercept? Now this one's a bit weird because we don't have any numbers, so we're just going to work with the letters that we have. We need to set y is equal to 0 because that's when our x-intercept happens. So we've got 0 is equal to a log base 2 of b x minus h plus k. And then we just do algebra just like we would do with numbers, except we'll do them with these letters instead. So minus k on both sides. Then we've got -k is equal to a log base 2 b times x minus h. Divide both sides by a, and we get -k over a is equal to log base 2 b x minus h. Now we need to get rid of the log here, and we'll just do that by rewriting this into exponential form. So the base of the exponent is 2. This is the exponent, and this is what it was equal to. Now divide both sides by b and add h on both sides. So we get that 2 to the power of negative k over a divided by b plus h is our x-intercept. We want to transform this equation here, which looks like it already has transformations on it. We want to stretch it vertically by a factor of 0.5, reflect in the x-axis, translate 5 units right, horizontally stretch by a factor of 0.5. We want a sketch of the resulting function. There's two different ways we could do this. We could use a table of values and mapping notation to figure out where the points on this graph went, or we could find the equation of the new transformed graph. Let's try the table of values first here. Let's get our mapping notation ready. So first we horizontally stretch by a factor of 0.5, so we'll say 0.5x, and then we translate 5 units right, so that will be plus 5. That's all that happened to our x values. Let's look at the vertical transformations here. Vertically stretch by a factor of 0.5, so this is 0.5y, and we reflected in the x, so there's a reflection here. And that's all 4 of our transformations. Now we can take every point here, run them through our mapping notation, and then plot them. So negative 3, put that in here. Negative 1.5 plus 5 is 3.5. Put a negative 1.5 in here, and it becomes positive 0.75. So do the rest of these, plot it, start the video again. So our new transformed function looks like this. Let's try to get the equation for it. So our original equation was y equals 3 log 0.25, 0.5x plus 2, all minus 3. Okay. Now to get the transformations in here, the y's are easy. They just need to go on the outside of everything, so negative 0.5. And I'll use big square brackets to show that it's outside all of this. The x, or the horizontal transformations, they need to go with the x right here. They don't split up, they go with the x. So right here we had 0.5, and now where the x is where we're going to put the horizontal transformations. So we had a stretch of 1/2, and then we had 5 units to the right. And that goes in place of x. Now we still have this plus 2, and we still have the minus 3, and then we're closing this whole thing with a big square bracket. And that looks pretty messy, so we'll want to clean that up. Y is equal to, just multiply this in to this term here, and also, it's hard to tell, but that's a different term back there. So this would be negative 1.5 log 0.25, and nothing ever happens to the base there. Next, the 1/2 and the 2 here can cancel. So we're just left with x minus 5 plus 2, so that's just x minus 3. And then this times the minus 3 over here is plus 1.5. And there's the equation of our transform graph. And now we could put this in our graphing calculators, get a table of values or the sketch from there. Example 3, what transformations would we need to apply to this function to make it into this much simpler function? Now you might be tempted to just do the same transformations that you see here in reverse order, but that's not allowed. We need to do stretches and reflections before we do the translations. So we'll have to figure out how to reverse this in the correct order. So number 1, let's undo this vertical stretch. So we'll need to vertically stretch it by 1/4. And then let's work through that algebraically and see how that would affect the equation. So we got a quarter, and it would be outside the whole function here. And the rest of the function stays the same. And now let's multiply in the quarter. There's one term here, and there's another term at the back there. So this would turn into negative log base 3, 0.5x minus 2 plus 5 over 4. Now there's a reflection here and there's not one here, so the next thing we'll do is get rid of that vertical reflection. And so we'll multiply this whole equation by negative 1. And remember, it goes into both terms here. And so it would cancel out the negative in the front here, but it would also go into the 5/4 at the back. And so, because that's a separate term, so now that would make it minus 5/4. Now to finish up with our vertical stuff, you can see now we've got to translate this up 5/4. And so we can add 5/4 outside the function at the end and cancel out with that one. So this one I'll just skip writing it. Obviously cancels out with that. Next, let's get rid of the horizontal stretch here. So horizontal stretch by, now this might be weird, but it's horizontally stretch this by 1/2, so that when we put it into the equation, it is a 2. And remember, it goes with the x here. So a horizontal stretch by 1/2 would give us 2x inside this function. And that would cancel. So we'd just be left with y equals log base 3 of x minus 2. And the last step, horizontal shift or translation, 2 units left. So then inside this function, we would put a plus 2 here with the x. It would cancel out with the minus 2. And now we're left with the function that we wanted. The function drawn in green has been transformed to obtain the function drawn in blue. And we want to know what is the equation of this blue function. And we're given that there's no horizontal stretch or reflection, or b is equal to 1. But there could be an a value and an h value and a k value. Let's just look at the graph and see if what we can determine here. We know the vertical asymptote was at x equals -4 originally, and now it's at x equals -6. So we've obviously shifted this graph left by 2 units. So we know that h is 2. See what else we can determine. From here, if we look at this x-intercept, we know that we shifted it left 2 units, so 1, 2, and would have been there except we had some vertical transformations happening. But this is a special point because the vertical stretch and reflection can't affect it, because we're always stretching and reflecting about the x-axis. So the only way that this point could get up here is a vertical translation of 2 units up. So our k value is 2. And now we're just left to find a. So I'm going to rewrite this equation with the things that we know so far. And now we'll just find a point on the graph and use that to solve for a. So we could use -2, 1. And it's nothing special. It doesn't have to be a point that's on both graphs. That's just random coincidence. So we'll put in 1 here for y and -2 for x, and then we'll solve this. So -2 on both sides here gives us -1. Now 2 to what exponent gives me 4? Well, that would be 2 squared gives me 4, so this is a times 2. Divide both sides by 2, and we get that a equals -1/2. So the equation of this blue graph is y equals -1/2 log base 2 of x plus 6 plus 2. List the transformations needed to turn y equals log base 2 of x into the blue function shown on the graph below. So probably the most obvious thing to start with here is it was reflected in the x-axis because, I mean, it's facing a different way. Now, once it's reflected in the x-axis, this point here will now be down here, this point here will be up here, and our vertical asymptote will still be at x equals 0. But it will look something like this here. Next, we can see that this point here is 3 units over. This point is also, looks like that point is as well. This point is 3 units over as well. And so all we need to do is to shift or translate 3 units to the left. And that would be it. There's a logarithmic relationship between butterflies and flowers. In one study, it was found that the number of flower species F is related to the number of butterflies B using this equation. How many butterflies would you expect to see at a location with 25 flower species? Well, they're giving us our F. So F is equal to 25, and we need to find B, the number of butterflies. So all we have to do is put this into our equation. It's given to us, so there's not much work for this question. Let's add 2.641 on both sides, 2.641. So we get 27.641 is equal to 8.958 log B. Let's divide both sides by 8.958, 8.958. And then we get that log B is equal to this. Now, to get rid of the log, we just rewrite this into exponential form. Remember, the base here is not written, so by default it's 10. So the base is 10. This is our exponent. And this argument of our log is the answer. So we just put this into our calculator and we get that there should be about 1,218 butterflies at this location. This was part of Relations and Functions 9, Graphing and Analyzing Logarithmic Functions. Here is some questions. Try them out. See if you know what you're doing.